Thank you, Jim. It's a great honor to give the Innis lecture, and I appreciate the invitation. And thanks to everyone here who's giving up beer and a warm patio to listen to me, which is, we could all call it off now and go if you like. But unfortunately we can't. So in the last year and a half, we've seen the financial world kind of turned upside down. We've seen commodity prices plunge. We've seen a housing bubble burst. We've seen the credit crisis and now a deep recession. And while I was watching this, I must say I'm kind of jealous of macroeconomists, because during all this time, I'm searching through the Globe and Mail and other places for interesting things, new things to say about either international trade or environmental economics. But macroeconomists have had basically the mother lode or the gold mine of research questions dropped on their lap in the last year. So in my deepest, darkest hours of what I might call macro envy, I came up with an idea. And the idea was I could write a paper on environmental crises. Now, this wouldn't make me a macroeconomist, and it wouldn't solve the credit crisis, but it would mean that at least I could publish a paper in 2009 with crisis in the title. Now, apart from petty jealousy and blind ambition, which have served me well in the past, there were also two good reasons for doing it. The first reason is simply that the credit crisis and the resulting recession should make, or has made, many of us rethink our understanding of the economy, specifically our understanding of low probability events like crises. The credit crisis has come as a surprise to most, if not all, economists in academia and in government. And I was thinking that if macroeconomists of the stature of Ben Bernanke could be surprised by the speed and the severity of the credit crisis, then surely my own views about the riskiness of an environmental catastrophe in the future, maybe those need to be revised as well. Secondly, unlike macroeconomics, environmental economics doesn't have a model of crises. Macro has well-known models of banking crises and of foreign exchange crises, but environmental economics doesn't really have a standard model of crises. We have models that predict rent dissipation, we have models of extinction, we have models of welfare loss, but we really don't have a crisis model. So with those two good reasons and my jealousy of macroeconomists in general, I decided that I would try and write a paper on environmental crises. So today I'm going to give you kind of a midterm report on what I've found out and I've learned about environmental crises. I was at the past president's dinner last night, where it's customary for the past president to ask a question at the beginning, which leads to a discussion. So today we're going to start with a similar tact. And the question is, what do these things have in common? The rise and fall of the Easter Island civilization almost 1,000 years ago. The slaughter of the North American bison in the 1870s of the 19th century. The Dust Bowl that hit the southern United States and parts of Canada to the 1930s. The draining of the Aral Sea in Central Asia from primarily in the 1970s and 80s. That used to be bigger than Lake Ontario. Now parts of it are about as wide as the Rideau Canal. And then my favorite is the extinction of the passenger pigeon. In 1914, the last passenger pigeon died in the Cincinnati Zoo. The answer to the question is that each of these was an environmental disaster. Humans played a role in each case, and they were largely unanticipated. So the challenge is, are there any unifying themes present in all or even many of these crises? Can I construct a useful theory of environmental crises? And by useful, I mean, can it help us reduce the risk of suffering through a crisis in the future? So first of all, I need a definition. A crisis is a drastic, irreversible, and largely unexpected change in environmental quality that lowers human welfare significantly. So maybe we can rule out the passenger pigeon just on that case. And my conjecture that I'm going to try to argue tonight is that the anatomy of a crisis has two parts: a set of preconditions and then a precipitating event. There's going to be three preconditions. The preconditions are going to be weak governance, positive feedback effects, and tipping points. The precipitating event could actually be many things, and I've just listed 3 here. Trade liberalization. I don't mean to malign trade, but it could also stop a crisis, but it could be a precipitating event. Civil war or political conflict that affected the degree of governance, or just natural variation in economic activity. I'm not going to focus very much on precipitating events. I'm going to carry through basically one, which is going to be a change in the size of the economy. The method. Well, since there is no standard model in environmental economics, I kind of have an interest in being the person who invents it. So I don't want to stray too far. So I'm going to adopt the standard model we use to teach students about renewable resources. And then I'm going to show you this model, and pretty well there's no way to get a crisis out of it, so I'm going to have to amend it. And I'm going to amend it in 3 ways. After I do that, I'm going to analyze the determinants of a crisis. So the standard renewable resource model has natural growth plus harvesting. It determines the system dynamics. Typically, the productivity of harvesting is a function of how big the stock is or how dense the forest is. And welfare is maximized in this model by restricting harvesting in one way or another, because the resource is typically diffuse, maybe common property, it's hard to monitor. This is kind of what we show students, undergraduates, but it's also a representation of a steady state under the condition that the planner is sufficiently patient. This is a limiting case where the discount rate approaches 0. The model is basically called the Gordon-Shafer model after Scott Gordon, and I can't remember Shafer's first name. Someone might know. And there's just a couple of things I want you to see from this diagram. First of all, on the horizontal axis is harvesting effort, and on the vertical it's revenues and costs. The first thing I want you to notice is this funny total revenue curve that bows down. Now, it bows down basically because of the features of natural growth. This is a steady state representation, and if you apply too much harvesting effort, eventually you lower the steady state take from the resource. The second thing I want you to recognize or look at this is if you look at L star, in the limiting case of a low discount rate, that would be the first best. And L naught, I think it's not, is the open access case where total revenue equals total costs. So, not surprisingly, the first best is less than the open access. And I'm going to introduce a term, governance, which is going to be basically scaling back effort from the open access back towards the first best. Now, the Gordon-Shafer model is basically crisis-free. You could shock it, you could change prices, you could change input costs. You can get extinction out of it, that's true. But it's kind of an infinite type of extinction, takes a long time. You can get a most rapid approach path case, but that wouldn't fit my story of crisis either because there's no welfare loss from that. So this model I'm going to need to amend. And the ways I'm going to amend it are, first of all, the 2 most important parts of the model that need to be changed are kind of the biological assumptions. So I call this the Terminator properties of nature. Because the Gordon-Shafer model assumes basically that you can't kill nature, and like your favorite B movie action figure, the closer you beat them closer to death, the stronger they come back. And that's represented here by, if you look at the natural growth function, that there's positive growth all the way over here, and there's no minimum threshold. So and that's the case where you can drive the stock down to epsilon, you leave it long enough, it comes back. And then on the right-hand side, I've graphed percentage growth. So that's G of S divided by S. And what you see is that percentage growth is rising. That's the property that the further you push nature towards 0, the faster it responds. So those 2 together, when you look at it this way, it seems almost silly, although I have many papers that use exactly this model. So I better be careful here. The second thing that the Gordon-Shafer model has is it has basically a strong negative feedback. And by that, I mean, let's say that there's a shock to harvesting. So the harvest rises, the stock declines. When the stock declines because of the harvest, productivity falls in harvesting, which then lowers the harvest, the stock recovers, and then the harvest rises. So basically, you've got this nice kind of negative reinforcing cycle, so it will dampen any shock. I'm going to have to eliminate that as well. So the 3 steps to the crisis are, first, I'm going to introduce tipping points. Second, I'm going to introduce limited governance, because my definition has a welfare loss. So clearly, I'm going to have to put some limit on what government can do. And then I'm going to introduce positive feedbacks. So what's a tipping point? So many people have different views of tipping points, so I wanted to be explicit about this. A tipping point is where a natural system's growth dynamics change dramatically. Once a tipping point is reached, removing all human activity doesn't restore the system. So it's a feature of the physical properties of the assumptions. And it leads to potentially irreversible and often dramatic changes. So here's kind of 3 examples that people refer to when they talk about tipping points. One is, if this was the stock we were talking about was a fish stock, that there might be a minimum critical threshold population, so that if the fish stock was harvested down to some low level, then eventually some other species in the ecosystem could take over its niche and drive it out. So predator-prey interactions can lead to them. Everyone kind of knows this in their own department. It's like if you have too many labor economists, every new hire is a labor economist, right? I can't pick on macro all the time. So the second one is, if we were talking about global warming, then perhaps the melting of the Greenland ice sheet or the degasification of the oceans, the release of CO2 and other gases that are sequestered in the oceans. That would be a tipping point. Or minimum viable sizes for ecosystems, the idea that you can't grow a complete forest in a coffee cup. Okay? So how am I going to do this? Well, what I'm going to do is, I don't think that, I definitely know that biologists and climatologists and every other physical scientist I've ever talked to don't really appreciate having their entire field in one state variable or in one equation. So what I'm going to do is I'm just going to add another physical process. And this physical process is going to look like this. So to set ideas, think of this as a forest, okay? And the density of the forest is rising as we move to the right. And the natural carrying capacity is not indicated there, but it would be K. The physical process P of S takes away from natural growth. You can think of this as soil erosion. And as the forest gets less dense, we're moving towards 0, then erosion is lowering the net growth that the forest has. And eventually, as the stock gets all the way to 0, you're going to have the property, even before that net growth will be negative. So you could view this as soil erosion. You could view it as a competing species. You could view it as sea ice melt. There's various interpretations. But what it'll do is in the Gordon-Shafer model, is it will change our natural growth to eliminate one of those undesirable Terminator properties. Now nature can be pushed too far, and that is the tipping point T. But it also has another feature, which is quite useful. If we go back to the percentage rate of growth and we recalculate that, we now see that the growth function basically isn't purely compensatory as it was before. When we move back from K, growth at first rises, right? That's where we're moving up in here. But then at some point in time, the percentage rate of growth starts to decline. And in this model, where I've set K is equal to 1, the answer is it occurs at root T. So root T is the point where the percentage rate of growth starts to decline. T is where the tipping point is. And root T and T can differ by quite a bit. So for example, if T was 10% of the stock, then root T is 30% of the stock. And it's going to turn out that many of the properties of the model revolve around us pushing us not close to T, but actually past just root T. So limited governance. Governments are not perfect. Now, as an Albertan, I always find that funny. I find that funny because Alberta is always complaining about Ottawa. And then I also find it funny that it's plural, because I've only had one government my entire life in Alberta. So governments are not perfect. Regulators face monitoring problems, and the constrained first best might look nothing like what I showed you before. So what I'm going to do is I'm going to represent the limits of governments, as I said before, by a simple parameter G, which is going to be the extent to which the government can hold back harvesting effort from the first best. From open access. Okay? Now, this isn't entirely ad hoc. Brian Copeland and I have a paper that's coming out in the journal just this June, where we take the Gordon-Shafer model and we introduce a monitoring problem. And in that model, we find that the constrained first best, in some cases, has this property that it's sticky, that it's stuck at some fraction of the total labor endowment. So this isn't just a shortcut to that. There's additional assumptions. The two assumptions that are additional are that I'm going to take G as constant, both in and out of steady state, which isn't true of my paper with Brian. And also, I'm going to take G as independent of the characteristics of the economy. So I'm going to freely move it around while not altering other parameters. That's also not true. Positive feedbacks. What are they? Well, these are different in that they involve humans, and the interaction is going to be between the environment and the economy. Basically, it's going to be where greater human activity affects the stock, and it's going to raise the return to this activity. It's going to require action on the part of humans. So how to introduce them? Well, to get the tipping point, I added a physical process. Now I'm going to add another economic sector. It could be affected by the environment, that's possible. And I'm going to add price determination. So I'm moving away from the partial equilibrium model that typically the Gordon-Shafer model is written as. And I'm going to allow factors to move across industries. So in what I'm calling the crisis model, this is what positive feedbacks will look like. So if you have a shock to harvesting, the stock will decline. Now it's productivities, because there's more than one sector. They will adjust. Those in turn will cause price changes. Depending on how those two things interact, factors are going to move. Harvesting will be reinforced if positive feedbacks are positive, and harvesting will rise. Okay. 3 examples that are going to fit at least roughly the model that I have. One is manufacturing pollutes the environment, agriculture suffers productivity losses. This is an across-industry negative externality, and this will have a positive feedback effect. The more that manufacturing expands, the cheaper it will be for it to get factors from agriculture. Second one, hunting or gathering of natural species sometimes have positive externalities via search or other methods. This is another potential positive feedback, and this is a within industry positive. The overuse of irrigation. So I have to keep on reinterpreting the stock and reinterpreting the industries. Overuse of irrigation raises the salinity in aquifers, lowers the productivity of irrigation, can drive up the price of products, and if the price response is sufficiently strong, it can actually raise the demand for irrigation. So I am going to show you some simulations at some point, so I'm going to quickly just tell you what the assumptions are. There's 2. It's a simple 2-sector model. H will be harming, harvesting, or hunting. M is maize, that was the agriculture or manufacturing. Production's constant returns. Tastes are CES. And the model's constructed so that under the right parameters, it collapses exactly to the Gordon-Shafer model. My original goal was to change it so I could write it in terms of just 3 parameters, the tipping point, T, the government parameter, G, and the feedback effect, F, which you'll see later. I haven't quite got there. Okay. So now I'm going to tell you what my story is, and I'm going to tell you how we get environmental crises now, so if you want, you can go. So my story of environmental crises is pretty simple. There's going to be a shock to the system. The shock to the system will be ignored because of weak governance. The shock will then be magnified by a positive feedback, and the positive feedback with the magnification will push the economy past the tipping point. Weak governance will turn out to be a necessary condition for a crisis, and tipping points and feedbacks will be complements in producing the crisis. Okay? So to understand the different forces at work, primarily positive feedback and tipping points, I'm going to draw examples from the past, the present, and the future. And I'm going to analyze the effects in partial isolation. So my first case goes back to the past, and here, in this case, feedback effects are actually 0, and I'm going to look at the interaction of tipping points versus governance. So I think after Jared Diamond's book, everyone knows something about Easter Island, but I'll tell you anyway. It's a small island in the South Pacific. It was, quote-unquote, discovered by Europeans, Jacob Roggeveen, on Easter Sunday in 1722. When he went on land with a few people, what did he find? Well, there were 3 surprising things, I guess. First, there was a tremendous amount of monumental architecture, which included the statues or the moa that you see there, but also the ceremonial platforms in which they're built, the ahu. And so there's monumental architecture. That was the first thing. The second thing was the island was barren. There's no trees that were thicker than, I think his captain's log said, thicker than a man's wrist. It was a poor island. The soil isn't very good. Agricultural output looked low. And the islanders had no means for which they could build the statues or move large objects. Subsequent archaeological work discovered that there was something like, I think, 900 of the statues on the island. And the ahu platforms, there's something like 450 of them. An average statue is like 13 feet high, weighs 10 tons. The platforms themselves, even if the statues weren't there, would have been enough to create the mystery, because some of them were football field size platforms, mortarless construction, 4 feet high from the seaside, containing absolute tons of rubble. So the mystery of Easter Island was kind of twofold. One is, how did they ever build the stuff, given that there was no materials there for creating ropes or sledges or levers? And then secondly, the island was very poor, and the islanders themselves weren't in very good condition, and there wasn't very many of them. So how did this island society support and have the wealth to support an artisan class that could have built them? Now, in some sense, part of the mystery was solved in the 1970s by work by a paleontologist, Richard Flenley, who took core samples from 2 of the volcanic lakes. And a paleontologist looks at pollen records under an electron microscope, and he reconstructed the environmental history of Easter Island. And the history basically shows that when Polynesians first arrived, there was a large forest, a dense tropical forest on the island. There was many species of trees and plants, and that basically by the time, maybe 1,000 years later, this had been removed and entirely eliminated. Once it was eliminated, the islanders, of course, lost all their means for seafaring, and they couldn't collect fish, and they also lost all their construction materials, which is perhaps why the island's littered with moa and other construction. Now, that's all right, but an old colleague of mine, an economic historian, who I won't mention, said, well, that's not really an explanation, that's kind of more of a description. And he's right, because Easter Island is actually one point in a sea of data. Polynesians actually colonized the largest area on the earth of any ethnic population. And what you see there is the Polynesian Triangle. They came out of the Samoa-Tonga complex maybe around 1000 AD, no, sorry, 0, or even before that, and then they moved north, east, and south. They colonized literally hundreds of islands. So any explanation of Easter and its dramatic rise and fall really has to be within the context of the control group of the rest of Polynesia. And only if you have a theory that does both do you really have an explanation and not just an ex post rationalization. So this is where Jim and I come in. We wrote a paper in the late 1990s, and our story was basically that Easter Island was unique in Polynesia because of environmental conditions. It has a very slow-growing, what we call the forest soil complex, and that was true for 3 reasons: the type of palm tree that grew on it, rainfall, and temperature. We had an economic model, which was basically an extension of the Gordon-Shafer model that had Malthusian population dynamics. And surprisingly, within this model, if the resource grows slowly, then you get a boom and bust, which is the Easter story. But if the resource grows relatively quickly, you get a much more smooth transition to the steady state that we argued would fit the rest of Polynesia. So this is basically, what is this? State space. So I've got the resource on the horizontal axis. I've got labor on the vertical axis. It's a two-equation dynamic system. The first one I've kind of described, that the resource stock is growth minus harvesting. And then there's Malthusian dynamics, which are determining L. And the bright blue path is the one that we believe the Easter Island civilization took. They came to an island that had its forest intact. There was a small number of individuals. And then what happened then was that in the movement to the interior steady state, the unique and globally stable interior steady state, there was a boom and bust. And that when Roggeveen arrived, they had gone past through at least the first cycle, and the high population that was around 10,000, that was the population that helped build all the monumental architecture, and the resource stock being greater than what it is in the steady state, that's the forest soil complex before it was degraded by the Easter Islanders. Now, Jim and I gave this paper, everywhere, and there was lots of good questions, but these are three questions that I guess still bothered me, or were commonly raised. One is, what if there was some control over resource use rather than open access? Because that's what we assumed. And the Polynesians had some methods for restricting resource use. Second one is, where's the crash? I see multiple cycles. Did Roggeveen arrive at exactly the right time so that there was only one cycle? And then I used to have a colleague at Wisconsin who every time I went for coffee would kind of bother me and say, Scott, who cut down that last tree anyway? So now, let me take exactly the story that we had before and enter tipping points and governance. So this is exactly the model that I've kind of introduced with the tipping point, but with the Easter Island Malthusian population dynamics and governance set at open access level. So there's no governance here. So what I want you to see from this is, first of all, there's still one unique interior steady state. That's good. This is one isocline. That's another. And we still, under these parameters, have the cycling in, just as we did in the case before. But now the tipping point in this slide here is at 2400, and that's this dashed line. And through this tipping point down here is a steady state. Because if the stock is exactly equal to the steady state and the labor is equal to 0, nothing moves. If the stock was to grow slightly, because it's a tipping point, it grows. If it was to shrink, it would shrink. But the labor, if it was a bit higher, because we're to the left of this isocline, declines. So what that means is it's stable in one direction, unstable in the other, and it's a saddle path. Well, it's a saddle point, for which there is a saddle path that goes through it, which is the red line that you see there. So this figure, its sole purpose is to show you that the introduction of a tipping point creates a basin of attraction. And every initial point below the red line is going to cycle into the Easter Island story here, but any point above here is then going to cross the tipping point and crash at positive speed into the vertical axis, a true kind of a car hitting a brick wall type of catastrophe. So tipping points create basins of attraction. What about governance? What is its role? So now what I've done is I've altered the governance to restrict harvesting. And what you can see is there's two effects. First of all, as we move to the right, the steady state stock is moving to the right. So not surprising, restriction on harvesting raises the steady state and moves you further away from the tipping point. The second thing, though, is that the red line, which is the delineation of the basin of attraction, is rising throughout. And the reason for this is that the overshoot in terms of labor force growth is restricted by the fact that when they land on this big island, they're still holding back in their harvesting, and this is cutting down on the speed with which the labor force grows. So governance moves us away from the tipping point and kind of slows down or makes it harder for the overshooting behavior to occur. Now, if this was it, I probably wouldn't have shown you. I wouldn't have used this as an example. But there's an important property in these figures, and that is that all these steady states are to the right of the peak of that curve there. And that peak of that curve was the root t that I mentioned before. It's entirely possible for it to be to the left of root t, in which case the dynamics are now quite different. So the first proposition says that if the steady state was to the left of root t, which is kind of the point where you start pushing nature and it starts tiring out, it can't come back so fast, then the unique interior steady state is unstable. We still have two saddle paths. There's only one trajectory that enters the saddle path, and all other trajectories now crash. What it means is the dynamics now look like this. So in some sense, this kind of answered some of the previous questions. We now have a single boom and bust, right? There's only one cycle possible. The answer to my colleague who used to bother me, who cut down the last tree, is, well, once you pass T over here, the islanders can throw down all their tree-cutting utensils. Basically, soil erosion or the negative forces that are ruling the tipping point will eliminate the forest, and no one needs to cut down the last tree. So in some sense, this seems to answer those questions, but you know it comes at a cost. The cost is, if you look at the figure, that the tipping point, if I believe the parameterization that Jim and I set up for the model, which has the steady state at 6,000, and that was based on fertility parameters that we chose for Polynesian societies, the tipping point has to be big. Matter of fact, it has to be like over 30% of the carrying capacity of the island. So it has to be a very fragile ecosystem for us to get this. So at this point in time, I think tipping points are interesting. They create basins of attraction, and governance can work against them. They slow down overshooting. They can produce extreme outcomes. But tipping points alone, I don't think that would make a very good theory of environmental crises. Which means I better have something else. Which brings me to feedback effects. So here I've got a few examples. They're extinctions or near extinctions. So in the 1870s, or even before that, right after the U.S. Civil War, there was 10 to 15 million buffalo on the Great Plains of the United States. In a punctuated slaughter from 1871 to about 1883, all those buffalo were killed. Some were put in private ranches, so that there was only maybe 100 left in the wild. This slaughter on the plains was quite surprising for many reasons. One is that buffalo multiply quite quickly, actually a little faster than cattle. And secondly, if you look at the guy on the left, who I call Chuck, they're quite fierce things, right? So they're not easy to kill. Nevertheless, they were eliminated over that period of time. And I'm going to tell you about one positive feedback that was perhaps responsible for some of that story. The second one, also during the 19th century, but taking a longer time, was the elimination of the passenger pigeon. Now, I don't really believe the estimates, but everyone seems to think there was 2 to 5 billion passenger pigeons in the United States as late as 1800. And yet they were hunted to extinction between 1850 and maybe the last commercial hunt in 1890, and they were entirely extinct by 1914. So this is a huge mass extinction, and if we believe anything even close to the 2 billion, it seems almost unbelievable. Now these cases, both of them, although they're kind of similar, they're both in the 19th century, they operated on different parts of the United States. The passenger pigeons were basically on the eastern part of the United States, it's forested, and parts of Canada, whereas the last elimination of the buffalo after the Civil War was on the west. Now the positive feedback effects, when you read the history, in both cases have to do with these hunter externalities. So in the case of the buffalo, what happened was the buffalo hunters would go to where they were. They had their wagons and they had very powerful rifles, and they would just start to shoot them. The buffalo tend not to run away even though you're killing them, because you're at a great distance with your powerful gun, and you can kill maybe 100 or 120 in a stand before the herd breaks. But then the problem is you then have to rip off their hide and take their hide back to town. But once there was enough buffalo hunters, basically a new industry was created, which was freighting. And freighters brought wagon trains with as many as 50 oxen through the fields. And they would stop by the buffalo hunting camps, and then they would either buy the buffalo hides from them, or they would transport them for 2 or 3 cents a pound. This is basically a small non-convexity that only a large number of hunters and hunting activity could support, and it's going to work like a positive feedback. In the same kind of vein, but different, is the passenger pigeon case. They moved south in the winter, and then they moved north in the summer. And the real problem was finding where the nesting grounds were. An individual hunter, of course, or trapper, had no interest in telling the rest of the hunters where they were. However, the railroads did, because they made a good business on shipping all the passenger pigeon carcasses to the east. So when hunters brought in birds, they had their own trappers in the field, and by that information and the use of telegraph, they spread that. So basically, there was a search externality in the case of the passenger pigeon. Both of those are positive feedbacks. So what do feedbacks do? They magnify changes to the economic system to produce larger outcomes. Their strength is highly uncertain. They're difficult to measure. Even the stories I've got, they're kind of within industry externalities. We know those things are hard to measure. And they tend to produce multiple equilibria. 2 things about this. You're, of course, going to have to read the paper to see the model. But F is my measure of positive feedbacks. And it's the thing you're supposed to see about this is it's all parameters. It involves taste parameters, which are CES, that's the sigma, and then the 2 epsilons are basically the elasticity of the production functions with respect to the stock. It's useful that it's a parameter in that I can then move it around in simulations. But the second one is the way positive feedbacks work is that, let's say that there's a shock to the stock. The impact effect is that productivity and harvesting drops. But through the general equilibrium interaction, the amount of labor allocated to harvesting could rise. And that's what the second comparative static is. And it's negative because it says that if the stock falls, basically more labor will be put into harvesting as long as feedbacks are positive. But the extent to which labor is channeled through with the positive feedback depends not only on F, which I can parameterize, but also depends upon BM, which is the share of income spent on manufacturing, or actually the share of labor in that industry. And since tastes are CES, this is not constant. So the strength of feedbacks depends, the impact of it, the total impact is an endogenous variable. I said you get multiple equilibria, so I'd better find out whether we've even got one. So the second proposition says, if we set the tipping point to 0, and if we make this restriction, then we at least have a stable interior equilibrium. And this restriction is what you normally impose in the Gordon-Shafer model, so it's not different. So then I decided, then I did 100,000 comparative statics. You see, this Innis lecture is a lot of work, so you got to screen calls, let me tell you. So what I've shown here is there's a distribution over shocks, and the shocks in this case are just labor input, and the output would be the resulting steady state stock. Okay? But to make things a little bit confusing, and since I'm going to talk about the climate, I'm going to talk about climate eventually, I've translated the stock into a new variable S called climate, so that high values equal to 1 would mean that the stock is close to 0. So bad outcomes are to the right. With my 100,000 comparative statics, you see that with no feedbacks, I get a nice symmetric distribution, might be symmetrics. But as I add feedbacks, what you see is that the outcomes are shifting to the right because I'm basically expanding on the multiplier. With large feedbacks, I move even further to the right. And at this point in time, I think, this is great. It's great for 2 reasons. One, all I have to do is expand on feedbacks, and I can generate a catastrophe. And secondly, strong feedback effects and their role in creating catastrophes is a big topic in the climate change debate. So this is not mine, but this is from an article in Science in 2007. And it's very similar to what I'm doing here. So this graph shows feedback effects on the horizontal axis, and it shows basically temperature changes on the vertical. The comparative static undertaken is a typical one they do in climatology, which is a doubling of CO2 concentrations. So what's the long-run result on temperature from a doubling of CO2? That's what the formula is, dt, and it relates that with F being the feedback. So there's a couple of things that I want you to see. The first is, if we just even have a nice symmetric distribution over feedbacks, and the point of this article was to show that even a low probability of a strong feedback can mean that the distribution over environmental outcomes can have a very long right tail, right? That's the red one. So if we have very little understanding about the strength of feedback effects, then the distribution of climate change, the temperature changes from this experiment of doubling CO2 could potentially have cases where the possibility that temperature rises 5 degrees Celsius is not zero. Okay? Fat-tailed distributions like this have played a big role in a recent debate between Weitzman at Harvard and Nordhaus at Yale. Basically, Weitzman argues that fat-tailed distributions over the climate arise from not quite what I've shown you before, but for similar reasons. And that once you have those distributions, the expected cost of not reacting to global warming can be infinite. And he proves a dismal theorem. Nordhaus, on the other hand, says, well, you know, the distribution may be fat-tailed, it might be thin-tailed. Oh, and I guess here, fat-tailed is the student's T, thin-tailed is the normal. There's the, you can think of that. Nordhaus argues that the distribution may not be fat-tailed, and that how we value these catastrophes really depends on specifics of our utility function. So I thought that, you know, with the model, with the strength of the feedbacks going up, I could make contact with this part of the literature and perhaps generate a crisis. I can rewrite the model exactly in terms of their parameters, but unfortunately, the result is not the same. So what Proposition 3 says is it says that as you increase the strength of feedbacks, the impact effect of, in my case, it's not the doubling of carbon, it's the doubling or the increase in the labor endowment, that the change in the stock and the change in the implied climate is at first rising in the feedback parameter, but then declining. So instead of the long-tailed distribution that I showed you from the Science article by Rowan Baker, in this case, within the model that I've constructed, if we have a simple beta distribution over the F on the horizontal, the model generates the relationship in the right side, and then the red one is the probability distribution over environmental outcomes. So why is it different? Well, there's two reasons why it's different. First is, in their construction of their graph, they took a linear approximation around an existing steady state. And then they held that steady state constant as they varied F. But F is a parameter of the system. When I did it, as I varied F, I altered both the steady state and the effect. And what do we know? We know that, well, you don't know this, but as the feedback effect goes up, basically you drive down the stock. But as you drive down the stock, the extent and the strength of positive feedbacks starts to be offset by the negative feedbacks in the system. I showed you before that the impact of positive feedbacks was limited by or multiplied by the share of labor in the manufacturing sector. So as you steal more and more resources from this sector, that impact effect declines. And so the reason why the result is different is because positive feedbacks are self-limiting in an economic system. And they're self-limiting because resources come at increasing cost, and they're self-limiting in this model because nature responds more strongly as you push S towards zero when there is no feedback effect, when there is no tipping point. So feedback effects Well, now I'm really in trouble. The tipping points didn't work, the feedback effects were limited, and I had a personal crisis. So how am I going to get out of this? Well, here's what I'm going to do. Here's the recipe for crisis. I already told you in the beginning, a shock, poor governance, positive feedback effects, and a small tipping point. So let me put the two things together. Proposition 4. First, I'll show you the proposition, and then I'll show you an illustration of it. So basically, now I've moved away from the partial examination of each of the ones, and I've allowed for a positive tipping effect and a positive feedback effect. And the proposition says that there's a critical stock associated with a critical level of labor, and it's stable, and everything's fine at that stock. But if I increase L a little bit above that, then all of a sudden it goes away. Now, on one level, you might say, okay, well, that's not surprising. I have no limit on the harvesting. It's an open access case here. And that I know if I make the economy big enough, I might be able to get extinction. But there's two things you need to notice about this. One is that the parameter restriction here, this one here, would mean that as long as L is less than that, it means that in the absence of tipping points, you would always have an interior equilibrium. So I'm looking at variations that typically would not eliminate an interior equilibrium. Secondly, if you look down here, the critical stock is greater than the square root of t. But think back to the Easter Island case. When the critical stock was to the greater than the square root of t, everything was fine. I didn't have a catastrophe. So those two things together basically tell you that tipping points and feedback effects work as complements in creating crises. So here's why the Innis is so much work. I had to do another 100,000 comparative statics. So we're going to consider a once-for-all increase in the economy's productive capacity, and we're going to get these set of figures here. So the input figures, the input distribution is on the left, and that's the same one that I used before, right, when I showed you the feedbacks. So you can interpret this as shocks to the endowment, if you like. You could renormalize it on a mean, it doesn't matter. And that's 100,000 draws from just a simple triangular distribution. When you feed that through with no feedback effects, you get what you saw before. Weak feedbacks, you move down. Strong feedbacks, you move further. And then when you move left again, I added in a tipping point, and what do you see? Now the distribution over environmental outcomes caused by what I could argue is natural variation in the economic system, now the probability mass divides, and I'll argue this is an environmental crisis. Now there's two things you need to notice about this. Well, I'm not sure you can tell. Had I introduced the tipping point before, like in the no feedback case or in the small feedback case, nothing would happen. The distribution wouldn't bifurcate, okay? I do know, however, if I put in a big enough tipping point, it'll bifurcate. But we've already decided in the Easter Island case that wasn't credible, right? Because in fact, that's what I did there. The second thing you need to note about this is that the tipping point in here that's introduced is 4%. So the stock was normalized, so carrying capacity was 1. So big T is 0.04. This is a very small tipping point. The square root of that is 0.2. So what that might tell you is that from 0.8 to 0.1, these are the fact that a stock less than root T cannot exist, right? Because that's where nature's been pushed too far, and that's the Easter Island case where it gets to be unstable. But it goes even further than that. It goes all the way back to 0.7, which reflects the fact that feedback effects and tipping points are complements. So why is this a good representation of a crisis? First of all, it's a unique low probability event, right? A crisis is by definition unlike anything around it. A couple analogies. The Great Depression was not like the '81 recession on steroids, right? A nervous breakdown is not like your worst day at the office. An extinction is not like driving the cod population very low. there are discrete differences between a crisis and a non-crisis. Crisis is like pregnancy. You're either in a crisis or you're not. There's no middle ground. And that's exactly what this shows you. There is no middle ground, and that's what makes a crisis a crisis. Secondly, what else do we know about crises? They're difficult to predict and learn about, and they're difficult to learn from. So what do I mean by that? First of all, difficult to learn about. If I didn't believe in tipping points, but I had a full understanding of the shocks and I believed that there were strong feedback effects, then my economic model would predict a distribution that looked quite a bit like that, if you just remember 3 slides ago. And my economic model would do very well at predicting and understanding the economy here. But a complete understanding of that was absent of an understanding of tipping points would give me no understanding of this whatsoever. What does it mean that they're difficult to learn from? Imagine that you're in a crisis. You're collecting data. Maybe you're collecting data on many crises. What's true? What's true is that the set of the value of the forcing variable, which in this case is labor, that drives you to crisis, has huge variance. So if you were in crises and you were to look back and even correctly identify the forcing variable, you'd see great variation in it, and from that you might think it had nothing to do with the crisis at all. Matter of fact, you might pick some other variable that was correlated with it that had nothing to do with the crisis. The last thing is crises are costly or impossible to reverse, right? I guess with the financial crisis, that's pretty obvious, right? But extinctions, you can't reverse. Extreme global warming could be reversed potentially with geoengineering, but that'll be very costly. So one feature of the crisis is that it's impossible or costly to reverse. And why is that? And the reason why it is because you crossed a tipping point. And once you cross that tipping point, basically the rules of the game change. That even absent human behavior, something significantly has to move you back. And that's why it's so costly. So from putting it all together, what do I say? The probability density over environmental outcomes, it's not fat-tailed, like Weitzman wants us to believe. And it's not thin-tailed, like Nordhaus wants us to believe. I think it's discontinuous. The crises are unique events, and they're not well described by a continuous probability density function. And that neither tipping points nor positive feedback effects have to be strong individually, but since they're complements, they can easily create a crisis. What about the future? Well, there is future in the title, so I had to say this. So what would well, I have to pick a crisis, so I'm going to pick the climate. What would a future climate crisis look like? Well, I think a temperature increase of 5 degrees Celsius is pretty well what a crisis would be. The truth is we probably don't understand what the world would look like past 3 degrees Celsius, but 5 would certainly classify as a crisis. It's not viewed as a likely event, but it certainly would be a catastrophic event. What does the model tell us? Well, let's look. I said that the anatomy of a crisis had 2 parts, the preconditions. Governance is low. The Kyoto Accord is a failure, right? We all know that. Not only did Canada not meet it, but many countries are excluded. And whether something will happen in Copenhagen in December, we don't really know. But even if something significant does happen in Copenhagen in December, carbon is an extremely long-lived pollutant. Let's say I emitted a ton of carbon on the jet that I flew here. In 10 years, 70% of that carbon is still in the atmosphere. In 100 years, 35% of that carbon is still in the atmosphere. And in 1,000 years, 18 or something like that % of it is still in the atmosphere. So what this says is that in the Easter Island story, you could move G and move out of the basin of attraction. But when you have a long-lived pollutant, it makes it much, much harder to do that. In the case of the climate, positive feedbacks are thought to be strong, but they're not exactly the type I've got. They're typically physical positive feedbacks, like the sea ice melting or the tundra releasing methane. And tipping points exist. The elimination of the Greenland ice sheet, the melt of that, would definitely be catastrophic. I've calculated, however, there's one positive benefit to that, because Calgary would then be the second best department in the country, because everyone else would be underwater. So there's Western and then us. So I'm going home and driving my SUV around the block. But there's also the release of methane from the ocean. So there's these strange molecules that are in the seabed called clathrates. And there's a huge, vast quantity of these. And if these are ever released, and they've been released sometime in the past, their global warming potential is greater than the sum total of all fossil fuels that we have. So it's just absolutely a nightmare phenomena or scenario. So the preconditions are met. What about the precipitating event? Well, here's a few facts about CO2. And these are taken from ice core samples. So during the last 800,000 years, CO2 has varied. It's varied quite a bit. But it's varied between 170 and 300 parts per million. Actually, most of the time it was between 180 and 280. It's currently at 385. Well, I don't know, that may or may not make you nervous. But the second one is quite stark. Increases in the CO2 concentration in any 1,000 years were always less than 25 parts per million. 1,000 years. But in the last 10 years, it's gone up by 25 parts per million. So if you were to go back to the start of the Industrial Revolution and look at the speed with which we put carbon into the atmosphere, you kind of have to come to the conclusion that we're conducting a drastic planetary experiment that is, unprecedented. But do I believe we'll have a climate crisis? No, I don't believe we'll have a climate crisis. But 18 months ago, I thought AIG was a great buy at $40. I thought the U.S. housing crisis was a blip. And I thought the probability of the U.S. government owning major portions of the banking, insurance, and now auto industries, the probability of that was 0. And that is environmental crises, past, present, and future.